1. What's the freezing point on the graph?
D.
D is the freezing point.
Yes.
All right, D is in dog. Just because it's backwards doesn't change anything. The solid is still going to be at the bottom. The gas is still going to be at the top, right?
Right.
Everybody's good with that, right? All right. So D is still the freezing point because it's still in the same spot. Where is the liquid cooled at? See, and notice I said cooled and not warmed because the graph is going down. All right, Sophie, put your phone up. What's the boiling point?
B.
B. All right, what's surface tension?
Is tension on the surface.
Tension on the surface. If this was a first response quiz tomorrow and I asked you for that definition and that is what you gave me, would I give y'all any points? No.
Like when water molecules bond together.
They don't bond.
Okay.
They connect.
Say force, it pulls adjacent molecules together.
Cool.
Write it down if you don't know it. I wrote it on the board when we did our notes on that. It's a force that pulls adjacent molecules together. Okay, they're attractions. It's like magnets. They don't bond, they just attract. Okay? Now, what types of molecules have poor surface tension?
Non-polar.
Non-polar. Polar has good surface tension because they are stickier. They're going to have good surface tension because they attract better.
So slime.
Huh?
Slime.
Slime would probably be polar. Thinking about what goes into slime, I'm going to go with yes on that. No problem. All right, number 5. What are the 2 types of solids? Amorphous and crystalline. Now, how do you tell them apart? There's 2 ways.
They're
Hexagon.
torn apart by.
All right, well, if you say hexagon, that's because the crystalline have what kind of?
Crystal lattice.
All right, so a definite geometric pattern or a crystal lattice. So what kind of structure do amorphous have? If crystalline is a fixed pattern,
Random pattern.
amorphous is a random pattern. So fixed versus random, that's one way. What's the other way? Because I might ask this way.
Melts over a range of.
Which one melts over the range?
Amorphous.
All right, so how does crystalline melt?
At a set.
Very good. All right, crystalline melts at a set temperature, and amorphous melts over a range of temperatures. Okay, crystalline melts at a set temperature, amorphous is a range, and crystalline has a fixed arrangement, and amorphous has a random arrangement. All right, and number 6 goes with homework. All right, find the heat lost. How do we calculate heat?
Q equals
Q equals
T, CP.
M. Now, what in the question tells us which M we want? Do we have 1 temperature or 2 temperatures?
no.
None.
Okay,
Well,
we got none. So that tells us we don't want which one?
the one with the
The one with the
CP,
T and the
The one with the CP and the delta T because we have no temperatures. All right, so we either want HV or HF. Do I freeze and melt or do I evaporate and condense?
freeze.
So I want HF or HV? I want the F. All right, so my Q is what I want because it says how much heat. What's my mass?
35.6.
Okay, and where do I find HF at?
Blue chart.
So the blue chart, I don't have it in my hand. I think it's 334.
Yeah.
Okay, so when you look up HF, HF is 334. Q equals what when you multiply?
11,890.4.
11,890.4 what?
KJ.
Questions? Questions about how to do that?
Nope.
Everybody got it? All right, questions on the opening?
Nope.
All right, let's talk homework. Leave that up there. All right, so if we look at homework, question number. Nope, not checking it. That is fabulous. Question 1. 1,045 joules. Question 2. 250 calories. Question 3. 11,690 joules. Number 4. 192,100 joules.
Wait, what?
192,100 joules. 192,100 joules. 192,100. I'll work it in a minute. Number 5. 5,225 joules. 5,225. And number 6, 16,700 joules. Anybody else? Questions before we go over? Yes, sir.
Number 2.
All right. Number 2 is asking you to use question 1. Only use the specific heat of what?
Water.
Use question 1, but use the specific heat of water being 1 calorie. So in question 1, they're telling you to use what mass?
The one in the first question.
Yeah, so what is the mass of the first question?
5 grams.
Okay, so we're going to use the 5 grams. What is the change in temperature from the first question?
50.
Okay, and then instead of using the same specific heat from question 1, they want you to use the specific heat that they gave you in question 2. So what is the specific heat from question 2?
Hey,
What's wrong with that calculator?
I had 2 of them.
Oh.
I still want to make a bracelet.
No. Yo, Tomas. What's the specific heat in question 2 that they're giving you? In the parentheses. Yeah, the one in calories.
1 calorie over gram.
Yeah, so they want you to use the 1 calorie that they gave you in the parentheses. So you just put that there.
Hey, Miss Wall.
Hello. What
I
may I
know
do
you
for you?
miss me.
Huh?
I know you miss me.
Terribly.
This is snap. I'm in the bar. We got. That's for you.
Thank you so much.
Romano, she left.
All right. She's what? So 5 times 1 times 50 is what? 250. And the only difference in this question is because this is a calorie, instead of writing joules on the answer, you write calories. That's the only difference. Okay? It's just an English unit instead of a scientific unit.
I completely missed.
Yeah, that's all. Anybody else? Do you want me to do the one that you had a question about, number 4? Duffy? No? Yeah, 192,100. Celia. Which one? Sure. And number 1, it's asking you how many joules are given off when 5 grams of water cools from 75 to 25 degrees Celsius. How many temperatures do you have in that, Celia? 2. All right, so since there's 2 temperatures, you want to use this formula that I just used with Tomas. Okay? So, what do you do with the 2 temperatures they gave you? Subtract them. So, 75 minus 25 is what? All right, so I'm going to put the change in temperature right here with the delta T. So, that's going to be 50. Okay? All right, so they're asking me for how much heat. How much heat is Q? So, what's my mass that they gave me? Okay, so I'm going to put the 5.0 grams where the M is, right there. So I need my CP. You got your blue chart handy? All right. So what compound did they give you in your question? What? water. All right, so on your blue sheet, right here about where my fingers are. Can you see where my fingers are? All right, what's the specific heat of water right there? Yep, and so you're going to put 4.18 right here. All right, and then you're going to calculate Q. So punch that in your calculator and tell me what you get. You got what? That's the answer. And we put joules on the end. Okay, we're going to do the exact same thing in number 5. All right, so in number 5, tell me what you're going to put for delta T in that one. Yep. All right, tell me what you're going to put for mass. How much? Yep. And tell me what you're going to put for your CP. Yep. And then multiply again, and you got number 5. That's correct.
Are we gonna use the?
Are we going to use the? You said, are we going to use the, and you stopped.
The other sheet,
What other sheet?
the one that we was doing yesterday.
The graph? You're going to have to be able to read a graph on the quiz, yes. Now the back side, we're going to get to it when we get to 4.
Oh, I was about to say, are we doing this wrong?
No, we're going to do it in class for number 4.
So, I have a question.
Yeah,
So about the homework,
yeah.
whatever it says, like, when it's talking about water, we use that specific on our blue chart.
Yes.
Water.
Yes. Yeah, that's the nice thing about this topic with the state. The state took all that other extra stuff out for y'all. We used to do this with all kinds of compounds years ago, but the state decided in its infinite wisdom that we were only going to use what compound now? Water. So you're only going to get those 3 numbers. That's it. No. A whole chart with all kinds of specific heats and a bunch of heat of vaporizations and heat of fusions.
Boy,
So how do we like tell the things like?
It's either specific heat, it's either heat of fusion or heat of vaporization. It'll be one of those 3. So like in number 4.
Like I'm saying for like number 2. Oh wait.
So like in number 4, it said calculate the what? The heat. And how many numbers do you have there, Xavier?
oh, yeah,
Does it give you a temperature at all in number 4?
No.
No. So that tells you you're not using the formula that Celia just asked about. Okay? Because we're not going to need a temperature because it didn't give us a temperature. So we know we have one of these. The only question is, do we need fusion or vaporization? What word did they use in the question? Did they use evaporation or vaporization or melting? Steam. Okay, so that tells us it's what? Vaporization. So we need the V.
So you'll use fusion if it says melting
Or freezing.
or freezing.
What if it said like number 4?
It said condense. So that tells us it's vaporization. So the mass in number 4 is what? So we're putting 85 there. And then HV we find where?
On the blue chart.
And we only have one HV, so it's not like you can get them messed up. HV is what
I
number?
just kind of got confused on like telling which one.
Gotcha. You see the difference?
Yeah.
Okay, and then Q equals,
That's why I said something about number 4. I was just like,
and multiply those, and you get it. So what I said was 192, 100. I
yeah.
called that one out several times. It's the only reason I remember. And that's how you get the answer. Anybody else confused by the math before you see it on the quiz tomorrow?
No.
Because you will see it.
Take it tomorrow.
You can take it. The only time you can take it next week is really during lunch.
All right,
Well-
that works.
Well, I take that back. The quiz is short enough that I might be able to stay after school if you came right after school. Okay, as long as you don't, show up at 10 minutes to 4, I could do it right after school. Okay? You could do it at lunch or right after school. As long as I'm gone before 4 o'clock, we could do it after school.
Wow, what you got to do?
Dance recital practice every afternoon. I gotta be in Thomasville.
You
Monday.
dance?
No, my daughter takes dance. I don't take it, I don't teach it. Oh, I can use this. All right. So the reason we're not doing the quiz today is simply because I forgot that I put an equilibrium question or two on the quiz. And what didn't I teach yesterday? So rather than having you just get a couple questions wrong, I thought I better move the quiz to tomorrow. So
What's the quiz gonna be on?
everything through number 2 on the board. It's really not even Le Chatelier. Okay, so when I start talking about Le Chatelier in a few minutes, Le Chatelier is not on the quiz. That'll be on the next quiz. It's really just through the definition or a little bit into equilibrium. Okay, once I finish doing the definition in the 3 boxes, I'm done. When I get to what affects equilibrium, that's not even on the quiz. That's on the next one. But I don't need to know that now. All right. Let's change the color. Now, this topic is going to be with us this week and next week. Some of you have asked me, what's one of the hardest topics we do? And for some of you, part of this will be one of those topics. Only because we're going to do a little bit of it this week. We're going to do a little bit of it next week. And I'm doing the easy part of it first. Some of you are going to be like, this is the easy part? Yes, it is. Because next week, we're going to do the chemical equilibrium. This week, we're doing the physical equilibrium. I break it up into 2 parts, hoping to make it a little bit easier and less painful. That's the idea anyways. Now, equilibrium is a dynamic condition in which 2 opposing chemical or physical processes occur at equal rates. Now, in this definition, there are 2 important parts that we're going to refer to time and time again. I don't know why they brought me that crap. I'm not going to do anything with it.
What is it?
A note. Yeah, it is. Well, who's calling, but I don't care. Go away.
See,
I'm getting ready to move. Just making sure I didn't skip anything. Nope, we're good.
I just said important point.
Moss.
Okay.
Did you know you work 6 to 7 on Sunday?
Ah, he works what? Did you say 6 to 7?
Yeah.
PM to PM?
No, 6 a.m. to 7 a.m.
Oh, jeez. On Mother's Day. Oh,
I work.
on Mother's Day.
Oh, yeah. No.
You gotta fix. You gotta hurry up.
Oh, yeah.
Because me and Tyshawn.
What?
Friday, Saturday, Sunday.
Dang.
Where do you work?
Usually
6 a.m. to 7
Usually
p.m.?
put me 6 to 6.
You better have
It's
3
Mother's Day, so
breaks.
it's-
I thought you're not allowed to work over that many hours.
Well, you're not allowed to work over 10 hours in a day, and I think it's 40 hours in a week.
Man, you know they don't
And
care.
that's child labor.
Dang.
No, yeah,
They
they really don't care.
I used to work
You're
at a
not
doctor.
You're not allowed to work how many hours per week?
40.
40.
Yeah.
They're not going to exceed 40 because they're not going to pay overtime.
Yeah.
All right, so,
Wait, I think.
well, then they're paying you overtime, but most places are not going to exceed enough to pay you overtime.
It was only a couple seconds.
Come on.
Why everybody's
More
mad?
people want that.
All right, so when you get this written down, what are the two important parts of that definition that I'm going to harp on this week and next till we get to?
Opposing chemical.
All right, you have to have two opposing, okay? Now, opposing means what? Opposite. You have to have two opposite reactions. If you don't have two opposite reactions, you cannot ever get to equilibrium. Okay?
Not ever.
Ever. Okay? So if I hold an ice cube in my hand, standing here in this classroom, what is the ice cube going to do? Is it ever going to refreeze standing here in this classroom? No. It will never, ever achieve equilibrium.
I know. Not ever.
Okay? If I put it in the freezer, it will melt and refreeze as it sits in your ice tray. It will achieve equilibrium over time. Now, what is the other important word or phrase in that definition? Nope. Nope. Equal rates. Okay? You have to have opposite processes, and they have to get to the point that they're at equal rates. Now, the other stuff is just sort of extra. Now, the part that a lot of people miss in this is that we will do both a chemical and a physical process. Today, we're focusing on physical processes. Okay? Today, are you listening? Today, we're talking about physical. Next week, we're going to talk about which one? Chemical. We're going to look at our chemical equations. We're going to do the math with the chemical. And y'all are going to be like, I like this, Miss Wall. That's easy. I like this calculating stuff. I can get these questions right. And then the next day, I'm going to come in and I'm going to give you a whole set of rules. And we're going to start shifting left and right. And y'all are going to be like, y'all going to hate me and want to use an expletive. Maybe several expletives. Okay? Because that's a swear word. Because then you're going to be like, I don't know what I was talking about. This don't make any sense. None of this makes sense. Who created this stuff? Okay? But today we're going to do physical, and physical's the easy part. Okay? So let's talk about it. Now, we're only going to do one physical process. And like I told you, we're close to the exam. And this rally just stole another day to prep for the exam that we're not making up. So, because we're not making it up. The curriculum, we're not making it up. The curriculum calls for the example to be evaporation and condensation. That's the one I'm teaching. We could do this with melting and freezing or sublimation and deposition. But since your curriculum specifically lists evaporation and condensation, that's the one I'm going to talk about. Now, this is in a closed system, meaning nothing in or out. Okay? Nothing goes in, nothing comes out. So, we know that the water molecules in here are doing what?
Moving.
They're moving. Okay? When they have enough kinetic energy, they will break the surface of the liquid and become vapor. Now, if those particles break the surface of the liquid and become a vapor, what process have I just described? Try again. Yes. Okay? Evaporation begins.
You know, I like the notes, but we didn't have to write a whole essay.
Yeah, I know. You're not going to like today at all. Just saying. So, if evaporation is beginning,
Let's say, so for example, could that be like a pot and Kool-Aid on there?
hold that thought until right here with boiling. Okay? That's what we have to learn about this to talk about boiling. All right? Are we at equilibrium? All right, before you answer that, think about the two requirements. You have to have two opposing processes, and you have to have equal rates. All right? So,
You ever thought about guided notes?
have I ever thought about guided notes? Let me think about this. I've been doing it 27 years. Have I thought about guided notes?
Probably not.
I have, and I chucked it out the window because I like my method better.
I do too.
You have to write it.
You don't know it.
Yeah, I like writing it.
There are lots of arguments we can have about which way works better, which way doesn't work.
Oh,
We could
sometimes
have
they can
conversations
say-
about whether you should work on a computer and whether I should teach
Oh, no.
and all kinds of other
That's
things.
not what
Okay.
Oh, no. Yeah, no thanks. I'm fine. No.
We could talk about test scores for me, for other teachers, and various things.
Hey, Duke
Let me
said-
just say that my way works.
Duke said that you used to teach him.
I do. I've taught many people who are teaching in school.
Oh, yeah.
How was he as a student?
He was okay.
He was okay.
Did you talk like that?
Mr. Dukes has always been Mr. Dukes.
Who's your favorite?
He came through the line of KOC the other day.
Oh, yeah. Just say.
Oh, yeah. Miss Waller.
Oh.
Miss Balls, I call Mr. Hoover.
She talked to her. I said, like, Miss Waller. I said, Miss Waller.
Okay.
Oh, yeah.
He said he had all the girls in school. He
Right, that's what he said.
and then I saw a yearbook picture of him. I said no.
I was talking to her. He was just like,
So, are we at equilibrium?
Yes.
He said, I'm gonna fall things up in the middle.
Do we have two opposing processes occurring?
No.
As soon as you can say no, the answer is, are we at equilibrium, yes or no?
No.
No, okay? If you can't name the two opposing processes, are we at equilibrium? No, okay? The answer is no, because there's only one process. What is the one process that is occurring currently? Evaporation, that's it. If we're only evaporating, we cannot possibly be at equilibrium because we are only evaporating currently. The water in that container is evaporating. Now, did I even put a temperature on this container?
No.
No, which is how we know it's evaporating. It can't be boiling because I didn't tell you it's at that one specific temperature. Okay? Because remember, boiling only happens at one temperature. Evaporation happens at a range of temperatures. All right, has everybody got what they need off this board?
Yeah.
Okay, so
So if you leave a cup of water in your house,
it'll evaporate out. Yep.
how long is it?
Depends on how much water is in there and what the temperature is in the house.
Full cup.
Gallons.
We're going to talk about those conditions in a little bit. All right, so evaporation continues. All right, so as evaporation continues, what happens up here?
Molecules?
Okay, molecules move, yes. The vapor continues to build up and increase, right? So, if evaporation is continuing, are we getting more vapor or less vapor? More vapor. So what's happening to my amount of water?
Disappearing.
It's disappearing, so the water is becoming more or less. Is everybody okay with that? Okay. So if I'm getting more vapor, what do the vapor molecules do to each other? They bump into each other, right? All right, the vapor, let's say collides instead of hits, collides with each other. Attracts and condenses back into the liquid state. So, what is happening now? Nope.
Yeah.
It's going back.
They got to their opposing.
Okay, so what's just beginning?
Condensation.
Okay, condensation. Begins. Are we at equilibrium? All right, I hear a no out there,
No, I
then I hear a yes out there.
You will hear a yes.
Okay, why is it a yes? Okay, so we have two opposing processes. Does it say they're at equal rates?
No. Oh, I was right the first one.
That's right. You were right the first time. We're not at equal rates. So, if we're not at equal rates, we're not at equilibrium. So we are still not at equilibrium yet.
So if you don't say that,
If it does not say you are at equal rates, you are not at equilibrium. The question flat out has to say you are at equal rates or you're at equilibrium for you to be there. Now, this is going to be very important next week when we do chemical equilibrium and you have to calculate. If it does not say the rates are equal or you're at equilibrium, can you calculate? No. Okay?
thank you.
Welcome. All right. So what now?
It's easy to identify equilibrium, whatever.
It will just flat out say we're at equilibrium. Yes, Ms. Whiteside. You want me? Yeah.
Jaden wants a bracelet.
No, I keep telling her she can't make a bracelet.
Look at
What do you mean?
Dude, I wanted to. Me too.
If you wanted,
Yeah, I just want to ask.
what?
Give me
Yeah.
Did you ask for it?
Can I have that apple? Didn't look like you was gonna eat it.
It's not messed
How
up.
is that messed up?
It's not messed up. That's just good observation. That's good.
I wasn't even thinking of it like that when I said she was.
Like, I'm messed up.
I'll make a rainbow too.
Me too. Me too. Come on. Come on. Come on.
Oh, you didn't sign it out. What's your photo?
Come on. You eat this whole thing.
I don't want that one.
So you got more.
I just be carrying that right.
She put it on. She was like, I'm going. She did that with baby.
Yeah.
Only like 2
I just
I put cereal in.
You should have just let her.
Might as well just let
I
it
was at Sheena's and I was like, she said, I need you to come home. Everyone got baby.
Oh, he wouldn't do that.
I was like, what?
No, bro, you would have been saying, look, I swear I would.
I love you.
You would have been fighting, bro. Yeah, bro, I would have hit.
They were you would have been there to say that.
Abraham,
He would.
Let me try.
I wouldn't want to fight you.
I'll put that fight.
No, but like, we've got the rest of the
Because he got a brother. His brother is go jump in.
If it was a one-on-one, I did. And he got longer, you say, I got
You don't want to fuck? I'm gonna put that down.
Oh.
Yeah, boy, I said right there, what you look like.
Like that kid. Oh my God. You know, Curtis?
Yeah.
And he did. Yeah. Oh. He
She's letting you
did.
every
No one
month.
else can do it.
I should still. Hey.
So, you know, some fruit. Like, he does that too. But, Curtis, yes. Curtis is good. And he like.
But hey, wait, is she gonna wear it? I should love it.
I've seen it, like, more fingers,
The whole thing.
Alright, we're going deep in there too. Well, yeah, try to do something on the first when we were.
Yeah, for Lily,
I was there, we tried to do something.
for Lily, I was
Wow.
You better sit
All
down.
right.
Do I look like a picture?
Do I look like I do good?
All right, so the last box. So we have some water. So how will you know that you're at equilibrium?
When it has two opposite processes and they're equal.
All right, and it will flat out do what?
Say it's the equal.
That's right. All right, equilibrium is achieved when the rate of evaporation equals the rate of condensation. Okay. And it will state that every single time for you that equilibrium is there. If it doesn't say that, then you are not at equilibrium.
yeah.
Okay, cool.
She's coming over here. Thank you.
Thank you.
I don't think I'm going. Where would you go?
Stephanie, what are you doing? Stop playing, we're in chemistry.
Some people are, everybody gonna get some. Why you not?
All right, are we caught up?
Almost.
Now, the thing to keep in mind about this is I said, what about evaporation and condensation? What's equal? The rates, okay? Now, when I said rate, this is the rate that evaporation these particles change into vapor. And the rate the vapor changes back into water. I did not say that the amount of water is equal to the amount of vapor. Okay? I did not say that. Okay? So you could have very little water and a whole bunch of gas, or you could have a whole bunch of gas and very little water. You could have any amount of water and gas. That's irrelevant. Okay? It's all about the rate of change. Sort of like going in and out of Walmart. Okay? In the morning, when people go in Walmart, are there a lot of people coming out of Walmart? No, because there's not a lot of people in Walmart. But at the closing of the store, there's more people coming out than going in. Okay? Pretend it does. Pretend it does for a moment. Okay? It's all about, equilibrium is all about the number of people going in and coming out at the same time. If 4 people go in and 4 people come out, the rate of entry and exit, if that's equal, then you're at equilibrium. The number of people in the parking lot and the number of people inside the store are irrelevant. It's about the rate of entry and exit. If that's equal, then you're at equilibrium. It's about the rate it changes from liquid to gas and gas back to liquid being equal. Yes.
So that's why water in the cup is the same.
Huh?
You said if I have water in a cup, it'll evaporate.
Yes.
That's that.
Remember, it's not in a closed system sitting on your desk. It's not in a closed system. On your desk, it's going out into the air and going wherever it wants to. This is closed, so it can't escape the container, which is why we're going to talk about your lid example here in a little bit. Okay? Shh, y'all stop. Because it condenses the air that's around the container. Yeah, it's just the air that's around it. Okay? Now, what 2 factors would y'all stop with those beads? I'm glad we'll be finished with that today. But the benchmark got in the way yesterday.
I had a benchmark.
Yeah.
I think one person would leave him alone if you let her make what she wants.
Well, I'm not. I won't give it in 4th period. I'm not giving it in 2nd. Now, in number 2 up there, the 2 factors that affect evaporation. How can we get something to evaporate faster? There are 2 factors that affect it. Above the heat. All right, increase the temperature. Okay? How else can we get something to evaporate faster? Can't remember if I said it in this class or if I said it in 3rd. But I said it somewhere in the last 2 days.
Then we definitely don't.
Right.
Humidity.
I barely remember what I had for dinner 2 days ago.
Pressure.
Moisture. What to start with?
What does it start with?
Wait, what are we in?
Light.
Condensation?
All right, let's use Andy. He's got to play tennis tomorrow, right? Say it rains before he's got to play and the courts need to be dry.
Surface.
Surface tension.
Surface
Surface
area.
area.
There you go. Got to increase the surface area. Spread the water out. You spread the water out, increase the surface area, it will dry faster.
Is that why, like, if you dry it in your hands, obviously it's like the dryer is heated, but if you like spread the water out.
Exactly. Spread it out. All right. Now, before you yell out something dumb, listen to me before I ask this question. When I ask you for the 1 factor that affects condensation, it cannot be temperature. Because we've already said temperature affects what? It affects evaporation. It's not the same answer for condensation. Okay? Now, as a gas, what affects the condensation in becoming a liquid again?
Pressure.
Tomas. No.
Climate.
What?
Climate.
What do you mean by climate? No.
Oh, no.
It was a hint.
The sun.
Give us
Is it a closed container?
Pressure.
The pressure.
Pressure's a no.
The volume.
Volcanoes.
Volume is warmer, but no.
Less surface area.
The size of the tire.
Not volume, no. Not pressure, no.
Give us a hint.
The size of the container.
Not size.
The water.
The amount of gas.
What?
Space.
Okay, it's got a name though. Okay?
I heard you say it. I tried to say it.
Space.
Quantities.
Okay, the amount of particles has a name. It's called concentration.
We was not gonna get that.
That's why I gave you credit for amount of particles. I knew you weren't going to know the name. It's a new vocabulary word. Concentration. All right, the concentration of something is the amount of particles. The more particles you have, the greater the chance of condensation. So when you have more gas particles up there, you have a higher concentration. Now, do any of you ever buy concentrated stuff and then dilute it with water? It used to be very popular to buy like juices in those rolled up containers in the frozen section and then add water. That's a concentrate. You can add water to
We
make
got
that
the
stuff.
Powder stuff.
The little powder stuff and you add water to it, same thing. It's a concentrate. Okay? I don't ever do that, but some people do.
I don't really like those.
All right. Now, your quiz ended here, by the way. Remember when I told you I had to get through a certain point for the quiz? The quiz questions ended here. Okay? They don't go through here. That started a new quiz. But tomorrow's quiz, for those of you who will be here who are not AP testing, they ended here. Sorry, I'm just telling you so you know. Because I told you we couldn't have it because I forgot we were done before that slide. All right, so Le Chatelier. Le Chatelier's principle. Most people say it looks like Le Chatelier, but it's Le Chatelier. He's French. It's French. Le Chatelier. All right, Le Chatelier.
You gotta get Sean to write this in.
And we're going to do him again next week, too. It all goes with chemical equilibrium, just like it does physical. All right? Y'all get your mind out of the gutter.
I'm about to say, y'all so negative.
All right? Le Chatelier's principle says, if a system is subjected to a stress, the system will automatically adjust to minimize the stress. Now, the stresses that we're going to use today only will be temperature. Next week, we're going to add in pressure and concentration. Okay, but for today, we're only going to do temperature. Pressure and concentration will add in with chemical equilibrium. All right?
Is Miss Hudgens 60?
Yes. So you don't want me to say things like that.
Oh, I hate her class.
I mean,
What did y'all do the other day in her class?
We just
grammar
review
review. That's like automatically.
like sentences.
Yeah.
We got this packet that we had to read.
You forgot to see.
No, I just sort of smushed it up in the
Did y'all write
air.
your vocab words?
No, we're not. She said we're not gonna have them until after our exam.
Good.
That was the second thing.
I
All right,
hope
we
she
caught
let
up?
us read today during class.
All right, so I'll schedule.
It's a whole discussion of the packet.
All right, I'm
Okay, I'm
done.
done.
All right, we there?
Yeah.
All right, so we're going to take that same system that we just talked about, and we're going to add a stress and see what happens. And we're only going to do this with temperature. Okay? Everybody there? Tomas, you there?
Yeah, I mean, I can remember it.
Okay. So if we take the first box, okay? If I increase temperature on the box, what's going to happen in that first box if I increase the temperature? Okay, the particles move faster. Okay. So what's going to happen when the particles start going faster? It's going to evaporate how? It's going to evaporate. Remember, I was at equilibrium. I was at equilibrium and I added that stress. So what happens to it? All right, let me put this in here. So I increase the temperature on a system at equilibrium. Why did I do that? At equilibrium. Because I just assumed y'all knew that, but maybe not.
Quicker than
Okay, so I was at equilibrium. I increased the temperature. You said the particles go faster. You said it evaporates, and I said it evaporates how? Quicker. Okay?
I said that, Miss Wall.
I know, but I was trying to get Xavier to say it. Okay, I knew you had it. It evaporates faster. Now, if it evaporates faster, what's going to happen in our box to the water and to the vapor? Okay? So, if it's evaporating faster, what's happening to our amount of water?
It decreases.
Okay? So, the water is going to decrease. And so, what's going to happen to our amount of vapor up here? It's going to increase. Now, I did not tell you to do that. All right, so catch up with me and see if that makes sense. Anybody besides me?
That's fine. It's whatever.
No, that's not fine. It's whatever, because you're going to see this on the next quiz. Because the lab on Monday is short enough for us to have a quiz on Monday or Tuesday.
That's
On Monday.
homework
You
tonight.
lost your-
Except that we can't do the makeup on Wednesday. So if you're not here Monday or you don't do your homework for Monday, we can't do the makeup Wednesday. For obvious reasons.
What's that?
We won't be here. Well, I mean, I haven't decided if I'm working, but the rest of y'all will not be here.
Are you not doing the walkout?
I'm not going to
My
Raleigh.
mom is. They might have to shut down the middle.
I mean, I would tell any young teacher or, halfway through their career, early in their career, that they need to go to Raleigh. I'm on the tail end of my career. I mean, I'm 27 years in. So
How many years have you been retired?
I have 3. I may have less, but I know I have 3 maximum till I can retire.
Miss Klein said that.
Miss Klein can retire. Miss Klein is well past.
Yeah, that's what she said.
With the amount of sick time Klein has, she is, I think, 2 years past. All right, so anytime you increase the temperature, you're going to evaporate faster. If you evaporate faster, what happens to the liquid in the pot? It gets lower, so you change to vapor. So does that statement make sense? Okay, so if you evaporate faster and you made more gas, what's going to happen up here? Okay? Whoops, I need to breathe. Okay? So there's more vapor. So if there's more vapor, what's going to start happening if there's more vapor? You're going to start doing what? Condensate. Okay? So you're going to condensate faster when the molecules start attracting faster. Okay? So, in our final box, yeah, will we get back to equilibrium?
Yes.
Yes. Okay, equilibrium will be reestablished. But what do you know about the equilibrium when it's reestablished? Will the rates be the same?
Yes.
Really?
No.
What'd you tell me about equilibrium or about evaporation?
It evaporate faster.
It evaporated faster. What'd you tell me about condensation? It's faster. So what can you tell me about the rates of equilibrium? They're the same?
They'll be faster.
They'll be faster. Okay.
Like
The rate of
Like the way that we want to say.
Okay. It'll be reestablished, but the rate of evaporation and the rate of condensation will be faster. They'll still be equal. They'll just be faster when they're equal. Okay? They'll just be happening faster.
Did you say this is like the thing that students like the least?
Yeah, they hate equilibrium.
But this is as bad as it gets.
No, the chemical one is as bad as it gets. The shifting left and right. This isn't bad. This is just boring.
Yeah.
I'm not dying.
I think it's pretty hideous to teach. Just because it's boring. I don't like to teach it because it's boring. I mean, I don't know how to spiff up equilibrium.
Is that what you were doing?
Pretty dreary.
I think you're right.
And it's only 11:05.
I know. Boiling is just as bad. I can't make it any better.
Okay, so what is the deal with our hall bathroom passes?
If you have all three, they're worth 15 points on your last test grade. All right. Now, everybody got it?
It's not your worst.
No, it's on your last. It doesn't matter mathematically in your average which one it goes on. So to make it easier on me, I just add it to the last.
So, like, what if you only have two left?
Then you get 10 points. All right. So what if I lowered the temperature? What would happen if I lowered the temperature here?
Evaporation would decrease.
The evaporation would decrease because the particles would do what? Move slower. So what would happen to my amount of water?
It'll increase.
The amount of water would increase and your amount of vapor would do what? Decrease. Okay. So what would mean here for condensation? There'd be less vapor, so I'd get more what? Or less what? Less condensation. So I would get equilibrium reestablished, but what would happen to my rates? They'd be slower.
Oh, slow.
Everybody okay with that?
Yeah.
All right. So why did I make you learn this? Well, yes, I have to. But the reason you have to is because we need to talk about boiling. I told you yesterday that boiling had certain conditions that go with it. Well, the conditions are why we have to learn about equilibrium. Now, a lot of people just say boiling is changing from a liquid to a gas. That's not the case. Okay? Boiling is the temperature at which a liquid changes to a gas when atmospheric, that ATM looked a little better, pressure is equal to equilibrium vapor pressure.
So the last one, pressure doesn't affect anything.
Nope, it didn't, because it's a closed system. So, if I ask you on the quiz, when does a liquid boil? What do you need to tell me? You only need the last piece.
When atmospheric pressure is equal to equilibrium pressure.
Yep. You do not boil until atmospheric pressure is equal to equilibrium vapor pressure. Now, in this room, we all breathe under atmospheric pressure. For those of you who remember your earth science, or you had to do anything with weather, or maybe you actually watch the weather every now and then, and they tell you about barometric pressure. If you ever watch the progress of a hurricane, and they talk about barometric pressure, all right? I lived on the East Coast most of my life until I moved to UNCG for school. I still watch hurricanes simply because my family lives on the East Coast. So if the pressure drops on the hurricane, I know the hurricane is strengthening. So that's atmospheric pressure. In order for something to boil, it has to equal at equilibrium vapor pressure. If these two things are not equal, boiling does not occur. So we need to know what equilibrium vapor pressure is, okay? Atmospheric pressure is just the pressure in the room. When you inhale, the pressure that's pushing on your chest, or you're just sitting here, the pressure pushing on your chest is atmospheric pressure. Equilibrium vapor pressure is our new pressure that we need to learn about, okay? Now, you'll have to bear with me while I draw some ugly pictures. So, that looks a little terrible. Let's see if we can't make it look a little better. That looks a little better.
It's a pie.
Oh, thank you. It's not as bad as I thought it was. I put some more water in. Now, I can't draw. I told you that. You have to put some bad pictures. Now,
That's not that bad.
so we're gonna have a pot of water on the stove. We're gonna heat it. We're gonna try to bring it to a boil. We're gonna do this on Monday. Only you're gonna do it with a beaker on a Bunsen burner.
You trust us?
Do I trust you? I'm going to. I'm gonna let you use matches. I'm gonna let you hook up a Bunsen burner. I'm gonna let you boil water.
Or pyromaniac.
We're gonna try real hard not to let you burn yourselves. If you burn yourselves, I've got burn cream and a Band-Aid.
If we burn ourselves, can we take a shower?
Nope.
So what do we catch on fire?
Yeah, I guess then you can.
Yeah, it's on fire.
The only thing I can tell you is
Your clothes.
I'll call 911 for them to come get you because I've got burn cream and a Band-Aid. If you burn your hair off, I'm sincerely sorry. It'll grow back eventually.
What?
I've had people do it. I can't fix it for you. Yep. Had one burn their eyebrows off. When I tell you not to put your head in a flame, don't do it.
Oh, that was.
People do it. Fire will burn.
It's
Don't lean your head into the Bunsen burner flame like an idiot. I can't fix that for you. Huh? Years ago. Okay? I can't fix that for you. Fire goes straight up from a Bunsen burner. If you put your head in the flame, your hair will catch on fire. I can't fix stupid. Now, where do you think I got it, or she got it from? Now, when you look at this pot, we need to talk about what equilibrium vapor pressure is, okay? So, you turn the stove on, right? When you turn the stove on, heat is transferred, okay?
From the eye.
Everybody should know this from another science class. This is not Miss Wall's class to teach, but some of y'all may not from your middle school science background. All right, heat is transferred from the stove or the eye to the pot, right?
Right.
The water moves faster. When enough to stove. I left out some words because I'm trying to make this fit in space. So put in the extra words. Okay? Two pot looks like, I don't even know what that looks like, but it says two pot altogether. All right? Water moves faster when enough kinetic energy, it evaporates. Okay? So we wind up with gas molecules up here, right? Now, these gas molecules run into cold air above the stove. So what happens with those warm gas molecules? Get that cold air. They do what when they hit that cold air?
They go back
Really? Y'all have seen tornadoes above your pots. I need to soak up your house. I'm dying to come to y'all's house just to see these things over the pot.
Steam over the pot. I cook ramen noodles.
You put pot on and the first thing you see is steam.
Water vapor.
Okay, when water vapor leaves that pot and hits that cold air, I'm asking you what happens to the water vapor. when it hits the cold air.
Like it disappeared.
Because it did what?
Because it got
Stop thinking about the pot for a second.
It got cold.
When any warm water is gas hits cold air, what happens to it? It condensates, okay? So the warm,
You should have done a shower analogy.
all right, the warm vapor hits cold air and it condensates. Okay? It falls back down into the pot. Now, if you actually feel around, don't touch the hot eye, but if you actually feel around the stove, how would the stove feel?
Warmer.
It will feel hot, yes. You're boiling water.
Slightly wet.
Slightly wet. Okay? All of that water vapor is not going to fall directly in the pot because it's not a closed system. So when the water vapor goes up and it hits that cold air and starts to condense, it's not all going to land where? In the pot. Some of it is going to land around the pot, so it's going to have a moisture around the pot, which is why I said you could feel that on the stove. Now, do not touch the eye because it will burn the snot out of you. But
And what happened to our eyes that can't see?
are you just trying to be a smart look?
The little heat thing.
Yeah, the eye of the stove. They're called eyes.
Oh.
Okay?
Yeah, it's doing it, what?
So, is it like single molecules so we don't see it?
Yes, they're itty bitty tiny molecules. Okay? Now,
Can I shut the door? Chris?
you can close the door. This process occurs repeatedly. Now, that means that this goes up and down over and over again, right?
All right. That's what you do.
Yeah.
That's how it's done.
These molecules above the pot create a pressure. It's called equilibrium vapor pressure. Sorry. Okay? So, what's going to happen as temperature goes up to that pressure? As temperature goes up, as temperature goes up, you get more molecules above the pot, right? So pressure increases. Okay? As temperature goes up, there are more molecules above that pot. So your equilibrium vapor pressure goes up. Now, so when's the water going to boil? All we're doing is talking about pressure above the pot.
When it,
When's the water going to boil? When it equals what?
the amount equal, the same rate of
Atmospheric pressure.
Atmospheric pressure.
The water will boil when the pressure above the pot equals atmospheric pressure. Now, is atmospheric pressure the same every day?
No.
Try to get off the phone. No, atmospheric pressure is not the same every day. So is boiling point the same every day?
No.
No, it's not. So when you guys all tell me the boiling point of water is what? or,
0,
try again,
32.
67, 48.
100.
130.
guys, when y'all said 0, that's the freezing point, okay? Which is why I said try again.
100.
I said, what's the boiling point? And they said 0.
don't use
And
Okay.
Celsius.
Right.
212 degrees Fahrenheit is fine. 100 degrees Celsius is what I was looking for. Okay, that's the boiling point of water. All right, so you need to. Your thermometers on Monday will be in Celsius. It will not be in Fahrenheit. So when you guys write down a boiling point on Monday, will everybody in the room write down 100? No. Will atmospheric pressure be the pressure that will give everybody in this room 100 degrees Celsius? Probably not. Now, most days I get things like 92 degrees Celsius. Is atmospheric pressure going to be such that I should get 92 degrees Celsius? No. 100 is an average, first of all. Okay? It's based on atmospheric pressure and 25 degrees Celsius. It's an average. We should all be in the ballpark of 100. Some of us might have 102. I've even seen as high as 104. I've seen as low as 98. I should not see 91. Yes. And the people who put down 75 and 86, what are y'all thinking? Okay? Boiling points are not that low. So if you have trouble with this on Monday, ask me. Okay? You should see rolling bubbles before you read a boiling point. If you see just a small bubble come off the bottom and a small bubble come off the bottom, it's probably not boiling. Okay? Now, to answer, he's not even in the room. All right? He wanted to know about putting a lid on the pot. Will putting a lid on the pot make it boil faster or slower? It'll make it boil much faster because it keeps the gas molecules in, which is going to allow that equilibrium vapor pressure to build much faster. So you're going to reach that atmospheric pressure faster. Okay? Now, let me ask you this. Again, we're going to have to work with a bad drawing. Very good. It's not that bad then.
That is a mountain. That's a mountain.
It's small.
Who thought it was
Oh
a
my
heart
goodness,
for a
I am
second?
great at, what's that? Dictionary.
We got that quick.
All right. So what have I drawn?
The regions in North Carolina.
The regions of North Carolina.
Right.
Yeah, the regions of North Carolina. You must have been pretty good at those games. I answered your question while you were in the hallway, by the way, genius.
About the lid
Lid on the pot.
It makes it boil slower.
Really? Just so you did the question wrong on the test. If we put the lid on the pot, does it make it boil faster or slower? Faster, because you are going to reach your equilibrium vapor pressure faster, which will get you to atmospheric pressure faster. Now, if we have the regions of North Carolina, will that affect our boiling point at all?
Yes.
Yes. Are atmospheric pressures the same across the state?
No.
No. Atmospheric pressure is not the same. Where's high pressure at?
The mountain. No.
Low.
Coast. The coast.
High pressure's at the coast. Nobody ever gets that. They always tell me it's high in the mountains. Okay? High pressure's at the coast. High atmospheric pressure's at the coast. All right? So that makes what at the mountains?
Low.
Your low atmospheric pressure is at the mountains. All right? We're in the middle in the Piedmont. So, does that affect boiling point?
Yes.
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 Remember, boiling point's all about atmospheric pressure. So, how does that affect boiling point?
Let's go slow.
It'll be lower in the mountains.
Yes, sir.
What will be lower in the mountains?
Pressure.
Pressure is lower in the mountains.
You need to reach lower
So the
pressure.
boiling point
It's gonna take longer.
Boiling point will be lower where?
in the coast.
All right.
The mountains. The mountains.
All right, hold on, since we're all guessing all over the map. Okay? Atmospheric pressure has to equal equilibrium vapor pressure to boil, right?
All right.
Atmospheric pressure equals equilibrium vapor pressure to boil. So boiling point is based on equilibrium vapor pressure and atmospheric pressure. Where is low atmospheric pressure? So what does that tell you about your boiling point? That's right. Wherever you have low atmospheric pressure, you have a low boiling point. So where you have high atmospheric pressure, you have a what? You have a higher boiling point. So, where's your food going to cook faster?
Oh my gosh.
The coast.
The mountains.
The coast.
If it has a.
All right, let me ask you this. Does food cook faster at a high temperature or a low temperature? So where's your high temperature at? So it cooks faster down here.
People would say in the mountains.
All right, and it cooks slower here. Now, if you ever look at the side of a cake box, it will tell you if you have a high elevation of usually about 3,500 feet, you have to cook it for an extra about 10 minutes. Why do you have to cook it for an extra 10 minutes?
Because the different atmospheric pressure.
That's right. It cooks slower at higher elevations. It cooks slower because it has lower what? It has lower pressure. Okay? Down here, it cooks at a higher boiling point or a higher temperature because it has higher atmospheric pressure. We're sort of in the middle. We don't have to worry about that. I don't know. You'd have to Google it. I have no idea. It would take longer. Okay? Everybody got it? There's not enough oxygen?
You know this, isn't there?
It may be. I have no idea. I've never looked. All right. The last thing we're going to do today, most likely, is a graph.
Okay.
All right.
It's very cold.
Equilibrium vapor pressure graphs.
Like, do you
Now.
have a source of air in here?
Like
Like a fan or a vent?
Is that a vent there?
That's it, it's right there.
Oh, I thought that was big. I guess that's.
I thought that was.
Well, I'm under. That's a vent.
Yeah. It's
All right.
I should have sat right here. That's what I was like. They're going right here too.
I feel hot. It's hot in here.
Now, the nice thing about the equilibrium vapor pressure graph is reading temperature and pressure is a breeze because every single person in this room has been in math class for, most of y'all are juniors. Do I have any sophomores in here?
No.
So I got all juniors and one senior. All right, have been in math class for 11 to 12 years. So, reading temperature and pressure is easy. If they give you pressure, you read to the line, you read down, you got temperature. If they give you temperature, you read up to the line, you read over and get pressure, right? Yeah. So, the only thing we have to talk about is how to find normal boiling point. Okay? Everybody have what they need?
Yes.
Because we have to learn how to find one point on this graph. Not hard. You got to know where standard pressure is. But y'all ought to remember because we just did the gas laws, right?
Yeah.
What was standard pressure?
One.
What one?
ATM.
Atmosphere.
Okay, just checking. All right. So, normal boiling point is the only hard thing to find on the graph. And as long as you can find standard pressure, you're home free. Okay? Draw a line across the graph at standard pressure. Okay? If the graph is in ATMs, use ATM, 760 torr, 101 kPa, whatever it happens to be in. Most of the graphs are in ATMs, not all of them, because you could have torr or kPa. Doesn't matter what it is, just read it. Okay? Now, the intersection of the lines is the normal boiling point. And we abbreviate that NBP. Because I don't want to have to keep writing out normal boiling point. Because we're going to have one tomorrow too on the phase diagram. We call it NBP. And we'll have an NMP for normal melting point and NFP for normal freezing point. Doesn't matter. I can record myself teaching for all I care. I'll teach to an empty classroom.
Don't do that.
I've done it. Will do it.
You have?
Wait, what?
But I had to be out for a sub.
You what? You recorded
That's
where?
different. Like you ain't never like had nobody show up and then you.
Oh no, I've taught for a sub, but I'll just record third for y'all. How many will be out tomorrow? 1, 2, 3, 4, 5, 6, 7, 8, 9,
But it's gonna be 1, 2,
10. Okay,
5, 6. I'm not coming.
that's still what? You're just not coming?
Oh no.
That's 10. Jade will be out, so that's 11. That'll leave us with what, 8? 8 stuff. I don't mind recording for 8 people. All right. So if we go back here, what unit do you want me to put on our? Oh, you're still writing.
ATM.
All right, you want me to do an ATM?
What you been recording for the 11 people that would be?
Yeah, but I don't mind doing it while I only have 8. I mean, they seem to be offended that I was going to do it for an empty room. I mean, I'm clearly going to have people.
This is why me.
If you did have an empty room,
No, I just do it. That would be cool. I'd have 2 planning periods
what
on
would you do?
Friday.
Sit down and read your book?
No, I just upload my lesson plans and other stuff that I'd have to do this weekend. Get that done. Set up the lab because I probably won't get it all done tomorrow first period.
All right.
All right. Look the wrong way. All right. So Tiffany said do it in ATMs. So let me make it ATMs. All right. Let's make one right here. Okay. Now, whenever you have this graph, draw in a line at one ATM. Draw it all the way across the graph. Okay. And you'll do the same thing on phase diagram tomorrow when I teach it. Okay? The intersection right here of the line we just drew in and your graph is the normal boiling point. Okay? That is the normal boiling point. Does everybody see how I found it? I drew a line straight across the graph at standard pressure.
Why did you say that was hard to find?
It's not hard to find.
I thought you did.
Well, only because it's just not something that's obviously written on the graph. You have to remember to draw in the line at standard pressure. If you forget that, which some people do on the test, some people don't study. All right, now to find the temperature, how would you find the normal boiling point? All you have to do is what? Go down, and that would be your normal boiling point. Everybody go with that? Now, you remember yesterday when I said to y'all, do not lose that graph.
Yeah.
It was on the back side.
Yeah.
Do you think you can find that piece of paper?
Yeah.
You really should be asking Xavier that question.
Right.
Xavier, do you think you can find that piece of paper?
Is this the one you talking
That would
about?
be the one.
This
Yes, very good.
I put it on my notebook for all of you.
Very good. All right, that back side is what I want to do right now. Very good. Find that.
Wait, which one? Oh, the one.
The back side. Now, which one?
I might need another lab sheet though.
Why?
I think I lost it.
Oh my God. You serious?
I might have. I don't
We
know.
just got it.
And you have to have it for Monday,
Oh, that one.
or you don't get to participate.
But you gonna give me another one, right?
I don't have any spare.
Yeah, because we friends, right?
Someone else?
If somebody can give me theirs, I'll go make you a copy.
Might have it. Just gotta check.
That's crazy.
I'm gonna make him
All
a
right, check.
copy.
Wait, I got it.
Never mind.
I got it.
Don't lose it.
I'm gonna clip it in.
Why? Well, as soon as it hits that,
They changed mine. So now I gotta close on Friday, open on Saturday.
You
And I
have
work,
another
then I've gotta work from 6 to 4 on Sunday.
oh, so you got a long shift too.
We don't be open.
Yeah, I got a lot. Dang, me, you work more than like.
All right.
I love. I mean, yeah, it makes sense, but.
No.
Are y'all finding me my answers on my graph?
Yes, ma'am.
No.
Of course not.
Oh, I think.
Oh, that means you're not checking homework tomorrow, are you?
Oh, yeah. Don't know, maybe, maybe not. Given as short as it is, probably not.
Wait, what did you say about where it boils at? Like, how do we know? Not the normal boiling.
The normal boiling point, you got to draw on a line at S2P, standard pressure. Define standard pressure, this one's in Tor, so you got to estimate 760.
Somebody's knocking on your.
Can somebody go open it?
Okay, I'm going.
Oh,
Hey, you
yeah,
done got up off my stool and then you open it up.
Go away.
Uh-oh.
Thank you, Ms. Phillips, how are you?
Hello, Miss Cole.
What do we do for this fine day?
Good morning.
It's a fabulous day to be alive.
It's a fabulous day to be alive and make an A in Miss Wall's class.
That was even better
Was
than
even
they
better?
did. What do you want to see today?
Take the roof off with an A. B plus?
We have some of those. We have some A's. We have some B pluses. We don't have as many as I'd like, but we're working
They're
on
on the way,
it.
they're on the way.
They're on the way. Yes. Karen. Ms. Phillips, please speak to you.
Sophie?
That one's right here. You're a
Samaria?
Yeah, I got her right there.
Okay. May I see you ladies just for a moment, please?
I know in my room? Yes.
In the corner.
The big fine. Anybody have a question?
I have no.
Nah, not yet.
Everybody found standard
I think
pressure?
I mine's on.
Drew your line in?
Thank you.
I have some stuff.
Hey, we done for today?
Well, other than going over the graph, what y'all wanna do?
Thank you.
I mean, I'd like to go over the graph.
You guys are teaching for another 5 minutes.
Well,
I have to.
I like to use all my time.
Wait for a deadline, okay? I will not be here, tomorrow, but you must put that in my box tomorrow. Are you gonna go tomorrow? Go ahead and deliver.
Yeah, I'll go.
Okay. Tomorrow, so do like a small, or medium.
But
Document.
that's for homework, because I don't think we're gonna get to go over it.
Oh, okay.
I would like to go over it, but we ran out of time.
Inner molecular forces. What is
It's
that?
very cold. Thank you, promise.
What's the name?
So.
It's actually Van der Waals forces.
Desk is in the corner.
Like dipole, hydrogen bonding, LDL.
I tell you what you do, put it in my chair.
Yeah.
Put it in my chair. Okay, thank you. Thank you so much.
Anytime.
That's right there. If you should put the shit. The cure was. He and like.
We done?
What is the normal boiling point be the same for all of them?
Yep, normal boiling point, you have to do what? Standard pressure, what we just talked about, you gotta throw in the,
I drew the line.
okay?
And if it's like this, then it'll all be the same number.
Nope, you gotta draw in your line at 60 and estimate, so, and my line won't be very straight on the board. So you'd find the point here and read down, here and read down, here and read down. You see that, Jaden? Sure, yes, you got it, or sure, no, Miss Wall, go away.
I don't get it.
They won't be too, dude. You see how I drew the line at 760 across there?
Oh,
Because you got
because that's
four
what
there.
118.
Yeah, because you've got 180 in the source, you gotta use number for 4. Alright, we've got about 2 minutes. Now, you didn't finish your graph. Finish your graph homework. The other worksheet I gave you is only Shapley A and shifting. Okay? It's only 8 questions. It is the answer increase, decrease. Ted is asking you which of those would have the strongest intermolecular forces. And then give it a shot based on what you think. It's not hard, and I'll explain it tomorrow. If you're not here tomorrow, your job is to be caught up in class for Monday. I know you don't want to watch YouTube. I get it. Y'all are honors kids. Catch up. Don't come in next week and be like, I wasn't here. I don't know how to do any of this stuff. I won't cut you any slack. You just play on your phone. I know that. I won't cut you any slack. All right? Well, you have a great time. So, so, fix it when you come back next week. The lab is Monday. When you get here, if you do not have your what to parts, procedure, and meditative, there's two of those. You do not get out of your chair.
You
just can't have that lab sheet. All right. All right, put my calculators up so I have them.